Hey, hi, am I audible, Jayashree? Hello, am I audible? Okay, so in the last class, in the last week, we eh, eh, am I audible to all? Hello,
Yes, sir.
okay, okay, thank you. Okay, so in the last week, towards the end, we talked about the differential form of the for the motion of fluid flow, that is the Navier-Stokes equation, and then from the Navier-Stokes equations we discuss the different form of the Navier-Stokes equation. Like for the fluid static, that what will be the equation for the fluid static, and then we uh, saw that when there is no, like the viscous term is negligible, then in that case the equation reduced to something known as the Euler's equation. Okay, so today we will do uh, again, it is Euler's equations only, but in a different form. Okay, so we will do the dynamics of inviscid flow. So what do I mean by inviscid flow? That inviscid flow means in the Navier-Stokes equation, the mu into Laplacian of V, that term is negligible. Okay, that means there is no viscous effect in the flow. Okay, that is what the inviscid flow means. Because in this week's class, all of you have gone through the lecture, and I think the first topic was the Bernoulli's equation. So essentially I will go into the details of the Bernoulli's equation, like the little insight of the Bernoulli's equation, and I will derive it formally using the Euler's equation. Okay, so the question which I am addressing here is that, let's say I have two points in a flow field. Okay, point 1 and point 2. I'm and let's say this is represented by a vector, that is the small vector element dl, where this dl in Cartesian coordinate system is equal to dx I cap plus dy j cap plus dz k cap. Okay, the question which I am asking is that, what is the pressure difference between these 2 points? And answer of these questions will essentially lead to something which is known as the uh, Bernoulli's equation, or you can say that it is the equation for the any inviscid flow. Okay, so in general the pressure P is a function of pressure P is a function of x, y and z, right, in general. So what is the total pressure? Like the P is a function of x, y and g, then what is the dP? That is something called as the total derivative. So the total derivative from the difference, from the partial differential, from the rule of partial derivatives, I can write it as the dP dx into dou x plus dou p dou y into dy plus dou p dou z into dz. Is that right so far? Okay, so I am interested to find what is this quantity dP between any two point in the flow field. Okay, like these two points are connected by a line, like a small vector element dl. Okay, this dl is a vector which is dxi, dyj and dzk. Up to this it is clear, and in general the pressure is a function of both x, y and z, and this dP from the rule of partial derivatives I can write it in this way. Okay, I think so far there is no problem, right? Now yesterday we saw from that Euler's equation that what is the Euler's equation in general. So Euler's equation, if I write, so in the Euler's equation there is no viscous term present into the Navier-Stokes equation. So what was that? If I write it as the x, okay, I'll write it in generally. So I have dou v dou t plus v is equals to minus 1 by rho gradient of P plus, let's say, some body force term B, where the B is the body force term. What will be the, like these equations in the x direction, what will be the x momentum equations for this without the viscous term? So in the x direction these will reduce to, okay, let me write it down. So what will be this in the x direction? So V, again here the V is equal to u I cap plus small v j cap plus w k cap. Okay, that we need to remember, and this is the Euler's equation, this one. So then what will be the equation in the x direction? It will be dou u by dou t plus u dou x plus v dou u dou y plus w dou u dou z will be equal to minus 1 by rho dou p dou x plus some body force, like the body force in the x direction, which is bx. Now I have dp is equals to dou p dou x into dx plus dou p dou y into dy plus dou p dou z into dz. Can I substitute the dou p dou x from this equation to here? Can I substitute it? So if I substitute it, what will be that? And in the similar way, like this is for the x direction equation. So in the y direction again the another term will come which will be the dou p dou y, and in the z direction it will be the dou p dou z, right? So if I substitute it, let's substitute for this term alone. Okay, so dou p dou x into dx, what will be this? Dou p dou x into dx will be, so if I do that, it will be minus rho into this entire term on the what is there in the left hand side. So it will be dou u by dou t plus u dou x plus v dou u dou y plus w dou u dou z, rho multiplied with this minus so I'm substituting this, so this will be if I substitute dou p dou x from here, that is a negative sign here, that is also negative, plus rho bx. Is that correct? Whatever I wrote, and this entire term is multiplied with dx. Is so far, is this clear to everyone? That I just substituted the dou p dou x term from the x directions equations of the Euler equation to the total derivatives term for the pressure. Okay, that means I substituted dou p dou x term from this equation into this equation here. Okay, so if it is clear up to this, so can I write it in this way again? So it is minus rho. Now for this term I can write it in this way, that it is dou u dou t plus v dot gradient of u. Can I write it in this way? This first term, this I am writing it as this. If you substitute this v as ui plus vj plus wk, and this a Laplace like gradient term, gradient operator here in Cartesian coordinate is dou x of I plus dou y of j plus dou z of k. Okay, so this into u will be dou u x by this plus dou u y j plus dou u dou z k. So this multiplied with v, what is v? Sorry, what is v here? V is equals to ui plus vj plus wk. Now if I do the dot product of these two, what will be there? It will be this, right? If you do the dot product of this, so this term multiplied with this term, this term multiplied with this term, this term multiplied with this term, so it will be u dou x plus v dou u dou y plus w dou u dou z. So this is right, like whatever I wrote here, there is nothing wrong in this. Okay, so that means again I will write it in a different, the same thing I will write once again. So what I am getting is that dou p dou x into dx is equal to minus rho dou u dou t plus v vector dot del u. okay, into dx plus I have the other term which is the rho, okay, here I have rho bx dx plus rho bx dx, where bx is the body force along the x direction. So far this is clear, right? Now in the similar way, what will be the dou p dou y into dy? Can someone tell me what will be this term? Again I have to write the Euler's equation in the y direction and then substitute the dou p dou y term from the y directions equation into the into here in this equation. Okay, so if I do that, what will be that? Like you should be able to tell it from here itself. So it will be minus rho, what is the velocity in the y direction, that is v, right? So dou small v by dou t plus v into gradient of v into dx plus rho by into dy, sorry, here it will be again dy, it will be dy. Like is everybody clear up to this point? I just substituted the Euler's equations which I wrote in the last class into the equation for the total pressure, sorry, the total derivatives for pressure in that equation, and I am substituting these dou p dou x, dou p dou y and dou p dou z term from the Euler's equation into the equation for dp. So far it should be clear, right? So what will be the dou p dou z into dz? Just so here the u is replaced by v from this to this, so here it will be with the w, because the velocity in the z direction is the w, so it is dou w dou t plus dot w into dz plus rho bz into dz. Up to this is everyone clear up to this point? Can someone respond? It is clear, right, up to this point? Okay, so then what is dp? Now I have to add these three terms, this one and this one, because dp is equals to sum of these three terms, right? So then I can write dp in this form. It will be minus rho dou u by dou t plus dou v by dou t, sorry, dou u by dou t into dx plus dou v by dou t into dy plus dou w by dou t into dz. Like I wrote only the first terms for these three terms. Okay, what will be the next one? It will be minus rho, fine, it will be v, so it is v dot dou u, v dot v dot grad u plus v dot grad v, grad small v plus v dot grad small w. So if I sum all of this, what will be that? Can someone tell me? So it will be this dotted with gradient of u plus gradient of v plus gradient of w. Okay, but there is a dx, dy and dz terms separately, so I can write it in this way. Okay, so what I need to do here, let me write it as it was, into dx plus v dot into dy plus v dot gradient of w into dz. Fine, up to this, plus I have rho into bx dx plus by dy plus bz dz, as simple as that. So up to this equation it is clear, right? Now let me move one step ahead. So okay, what will be the next step? So let's say for simplicity I will write these as term 1, okay, these as this entire thing as term 2, and these as term 3, right? So what is term 1? Term 1 is minus rho dou u by dou t into dx plus dou v dou t into dy plus dou w dou t into dz. Okay, so what can I write for this? Can someone tell me? I can write it in this form: rho into dou t of v vector dot dl vector. Is that right? So it is as simple as minus rho dou v vector by dou t dot dl vector. If you substitute dl as dxi plus dzj plus dzk, okay, so if you write this dx from here, dl from here, and then dou v dou t from here, it will essentially end up with this term. Like, it is very simple to see, there is nothing difficult in it. What will be the term 2? Here the difficulty level will come. So in term 2 I have minus so I have minus rho into so it is v dot gradient of v. So let me write it first: gradient u into dx plus v dot gradient v into dy plus v dot gradient w into dz. So I can common the v vector from all of this. Now if I common the v vector from all of this, so this gradient u, then dx, so dx, dy and dz are there, so I can write it in this format. It will be minus rho, just check if I can write it in this way or not, minus rho v dot gradient operator, okay, into v dot dl. Can I write it in this way? Because this is the convective term of the Navier-Stokes equations essentially, right? This term is the convective term of the Navier-Stokes equation, so this term, essentially this is coming this, okay. So see, it is the exact same term, there is nothing difference, just dotted with a elemental length vector dl, that's the only difference. Now I will use a vector identity. So this is essentially a vector, so v dotted with gradient operator into v, this is essentially a vector quantity. When it is dotted with this dl, it is a scalar, okay, but this entire quantity is a vector quantity. Now I will use a identity rule for this particular term, this v dot gradient operator into v. If I use a identity rule for this vector, it will be half gradient of v dotted with v minus v cross with del cross v, gradient operator cross v. Like, it is very easy to prove this, okay, this relation, that from this to this, like this is a typical vector identity, these things is a typical vector identity, okay, there is nothing wrong in this thing. So what is this term? This v dot v is what? Can someone tell me what is this v dot v? V dot v is simply v square, right? Okay, because it is the one vector dotted with the same vector, so it is half gradient of v square, where v is the modulus of v vector, okay, this v is the modulus of v vector, okay. So let me keep the, okay, and this quantity, this gradient operator crossed with the v vector is something called as the vorticity vector. Let me represent it by zeta, okay. So this is vorticity vector, okay. So what is this term then finally what I am getting? So finally what I am getting is this, is equals to half gradient of v square minus v cross xi. Is that correct? What I wrote? Fine, right? Up to that. So when it will be dotted with dl, now this entire quantity is dotted with dl. Okay, dl is again a elemental vector, that is dxi plus dyj plus dzk. Okay, so finally the term 2 is coming like this. So minus rho v dot del v dot dl is something like minus rho half gradient of v square, okay, dot dl plus, because there is a minus total, so it will be plus rho v cross zeta dot dl. Is that right so far, whatever I wrote? Okay, I think this is right? Fine. So up to this it is fine. Okay, so now let's come to the term 3, which is very simple. What is there in term 3? Term 3 is rho. Term 3 is rho bx into dy plus by into dy plus bz into dz. It is term 3. Okay, fine. Now here I will do a simplification. Okay, what is that simplification? I will say that let us consider gravity as the only body force term. Okay, let us consider gravity is the only body force term. So in that case, this gravity always acts along in the negative z axis. Am I right? Okay, so like what will be the term 3 in that case? So this bx is equal to 0, by is equals to 0, this bz will be equal to minus g. So what will be the term 3? So term 3 then reduces to, it will be minus rho g into dz. That is the term 3. So what are the assumption I made? That only the gravity is the only body force that's the fluid is experiencing. That is the only assumption, and because of that assumption, the entire body force term or the term 3